I built a cheap tool changer for 3D printers. And you will never believe how simple and cheap the tool changing mechanism is. The entire mechanism is purely mechanical without any additional motors. Let me show you how it works. The extruder comes into the dock, the gears grip the filament, and the extruder picks up the hot end. And when you're ready to switch filaments, the extruder brings the hot end back to the dock, the gears release the filament, and the hot end stays in the dock as the extruder slides out. It's that simple. Now, I wanted the tool changer ever since E3G came out with theirs, but it was too expensive. And nowadays, you will still have to pay $2,500 to $4,000 to be able to print parts quickly with little material waste, such as with the Prusa XL. Or you can accept the slow printing times and tons of wasted material and still pay up to $1,500, something I wasn't willing to do. So my plan was simple. I started with this printer that I already had and modified it until I built this prototype. My goal was to only use parts that I can 3D print at home and cheap hardware I can buy online. Now I've spent the last 6 months and hundreds of hours designing this tool changer. But did I actually design a cheap tool changer? There seems to be a lot of parts here. Is the mechanism actually simple? The whole tool changer looks a little bulky. And can this 3D printer print real parts? Well, to find out, let's go back in time and start from the beginning. Now, this entire cheap tool changer project depends on whether we can design the extruder that works. So let's start with the extruder. Here I have a metal clone BMG style extruder that I had lying around and never used. So let's start by disassembling this extruder. My plan is to reuse the filament gear, the bearing, and the pin. This will make it convenient because I can keep my current printer assembled for as long as possible in case I need to take measurements or reference something. So now the new parts for the new extruder are finished and printed. So let's assemble the extruder and then afterwards we'll talk through the changes that I had to make. Oh, by the way, like this video if you want tool changers to become cheap. And here we have the assembled extruder. Looks pretty nice. Now let's take a closer look. You will see that there's a cutout down the center, and this cutout is for the filament to slide in. Now remember, we'll be using one extruder for all of the hot ends, so we need to be able to slide the filament in and out. But there were some issues with parts fitting together. Take a look at this filament gear and bearing. Look at that big gap. In fact, the gap is so big that the bearing wobbles around. Second is with the tension lever. The tension lever is not going in, and so the filament gears do not fully close and engage. And the third issue is the filament gears are not centered around the cutout. It looks a little worse in the camera than in real life, but it's still off center. So let's make all of the critical measurements, reprint all of the parts, and reassemble the extruder together. And here we have the updated extruder that's assembled. Take a look. The gears are more centered, although not perfect. The tension lever slides in and out without binding up, and the bearing is staying put in place. And now we have an extruder that allows filaments to slide in and out to the filament gears, which means we're ready to move on to design the hot end. But before we do, why only one extruder? Let's take a look at this Prusa XL. It has an extruder and the hot end for every filament, which means every filament is loaded and ready to print. And it can quickly switch between colors and materials, and it will do that with the minimum waste. However, the cost of all of these extruders and hot ends quickly adds up. So how exactly do you lower the price without increasing the printing time and the material waste? Well, let's think about that. If we share hotends, that means we will have to purge the hotend whenever we switch filaments, and that's not going to work. To get minimum material waste, each filament will have to have a dedicated hotend. There's no way around it, which means we only have one option. We have to reduce the number of the extruders, and we need at least one, so the hotends must share one extruder. That's the way to design a cheap tool changer. So this means we are ready to move on to design the hotend. But before we do, I just want to say thank you to Nuno Santiago. You see, I reached out to Bondtech about a cheaper tool changer idea, but Nuno responded, "Why design another version?" In fact, from his experience, all the extra extruders and hotends usually just sit idle and don't actually print parts. What a waste of parts. Why not design a tool changer with only one extruder? This would be an interesting project. So thank you, Nuno, for all of your insights and the feedback you gave me and giving me the final push to actually work on this one extruder design idea. And now to the hotend design. So right now I'm assembling the filament guide, and which is going to guide the filament to the extruder gears and then from the extruder gears to the hotend. And I'm also going to add a pivot, which is going to allow the filament to move side to side so that the filament can slide around the gears as the filament is going in and out. And I'm going to add the spring, which is going to force the filament guide to rotate to the right, which is always going to put the filament against the fixed extruder gear. But here I ran into a problem. The spring rotates the guide too far to the right, which means the guide would always crash into the extruder, and this isn't going to work. Which means it's time to redesign the hotend. Now I'm still going to have a pivot, but this time I'll put the spring in the center, which means the guide will stay centered instead of being rotated to the right. But here I ran into the next problem. The guide doesn't stay centered, and I think it's because the spring is just too weak. But something did work better than the spring. And believe it or not, it was actually this PTFE tube. You see, it was flexible enough to allow the guide to move side to side, but still stiff enough to keep the guide centered. And conveniently, the PTFE tube goes directly into the hotend, which makes this a clean and simple design. And now that we made some progress on the hotend, let's move back to the extruder, because honestly, it still doesn't work. And the biggest problem is with this screw. You see, we want the tension lever to open and close automatically whenever we're going to be picking up or dropping off a hotend. And this screw won't allow this to happen. So let's begin by disassembling this extruder, then we'll build the next one, and once we're done building, we will go over all of the changes we had to make to this extruder. And while we're building this extruder, comment below what would you 3D print with the tool changer? I'm really curious. And here we have the new extruder, and it actually looks very different. So let's review the changes one at a time. First off, the filament gears are now on the bottom. Not only does this bring the filament gears closer to the hotend, it also makes it easier to automatically open and close the tension lever. But this also changes how the tension lever rotates. So to close the filament gears, we added this stiff spring that will push on the lever, and it will pinch the filament gears together. Now we also need to be able to control the tension on the filament by the extruder gears, and this is what this screw is for, it will control the gap between the extruder gears. And now one of the biggest changes is this new dowel pin at the top of the tension lever. This pin will allow us to automatically open and close the filament gears, which will allow the filament to get in and out of the gears. So to open the gears, you push on the pin to the right, and now the filament can slide in. And when you let go of the pin, the gears pinch together, gripping the filament, which locks the filament in place. Now take a closer look at this pin. You can see that it's at a small angle, and this will become critical once we start looking at how we're going to press the pin in the tool changer itself. Finally, we have an extruder and a Hotend that's ready to go. So it's time to put them on the 3D printer. Let's begin by disassembling the Hotend and extruder from the current printer. And honestly, I'm looking for something that we can do quick, simple, easy, and cheap. Just to test if this extruder idea will even work. I want to spend as little effort and as little money as possible in designing the tool changer mechanism and the way the extruder and the Hotend are mounted to the tool changer. And we'll start by mounting the Hotend. Now we're going to secure the Hotend with magnets. And it's because it's going to be a simple design, and I've used magnets many times in the past. Now I know it's not the best, they're not the strongest, but it will be good enough for this prototype. So to install the magnets, we'll align the polarity of the magnets, place the magnets on the Hotend, then move them to the mount, and finally press the magnets into the mount. Now the next thing we need to do is to precisely locate the Hotend to the mount, and we'll use dowel pins in the mount that will slide into a tight hole and slot in the Hotend. Now I know pins work really well to locate metal parts together. Unfortunately, this is not the case here. These plastic parts will have loose tolerances, and these plastic holes and slot will wear out pretty quickly. So I don't expect this Hotend to last for long. However, I'm hoping these holes will last just long enough to test out this extruder idea. Now also, as you can see right now, the fit is slightly tight, and this might actually work out pretty well. We'll see in a little bit. And at this point I will press in the pins to the mount with a hammer, and I'm actually able to use the exact same pins as on the extruder, and this is great because I don't need to buy another set of pins. Now the next step is to mount the mounting plate to the carriage, and we're going to use a separate bracket, and this is because this will allow us to quickly and easily update the Hotend and extruder designs without having to disassemble the carriage, which can take extra time. So with this carriage bracket, we can quickly swap out the mount plate if it ever needs to change, and all we have to do is loosen and then tighten these 4 screws. So that's why we're going to have these 2 parts instead of just one. And now it's time for a quick fit check, and the Hotend fits pretty nicely to the mount plate. So let's keep moving with the build. Next we'll attach the Z probe to the bracket, then the bracket to the carriage, then the extruder motor to the bracket, and finally the extruder to the mount, which means we can finally move on to design the dock itself. And we'll begin with this slider. Once again, we'll use dowel pins, the exact same dowel pins as before. And these pins will position and secure the Hotend to the dock. Now this slider with these pins is going to slide sideways inside the dock. And the slider will be spring-loaded, which will always slide to one side when it's not being pushed. And the slide will sit inside of this bracket, and it will be held in place with this plate that will be secured with 2 screws. And if we look closer at the bracket, you will notice there are 2 counterbore slots, and these slots will give us the adjustment we need in the Y-axis. Now we will also need this right angle bracket, and it will allow us to mount the dock to the 3D printer frame. Now it will also allow us to adjust the Z position and the X position of the dock. So now with both of these brackets, we can not only secure the dock to the 3D printer, We can also place the dock exactly where it needs to be because we have the XYZ adjustment ability. And now that we have all of our docking brackets, we can attach them to the 3D printer frame. Now getting them positioned in a line was actually pretty tricky, and it really took some time and going back and forth, and it wasn't a straightforward process. But eventually I got all of the brackets to align to the hot end and then secured them in place so they can hold the hot end in the right spot, and that will probably be good enough for now. Which means we're finally ready to do a quick hand test. So let's slide the hot end in, then slide to the side and pull out that extruder, and look at that, nice, the hot end stayed in place. Let's do this again. And now that the hot end docking is working, we can move on to the next step, which is to mount the bracket that is going to open and close the tension lever on the extruder. Once again, this bracket was also tricky to install to the frame, but with some patience it is possible. And now that the bracket is loosely held in place to the frame, we can align it to the extruder. So just gently and carefully move around the bracket until the pins align well. And what we're looking for is, as the extruder begins to slide in, we want the pins to engage at the right time. And once they do, we can secure the bracket to the frame and then do some dry fit checks to make sure that everything is working okay. Meaning the hot end will stay docked when it needs to stay docked, and the lever will open and close when it needs to open and close. Now it does seem like it's taking a lot of force to pull away the extruder from the hot end, but maybe it's just because I'm not able to hold everything precisely. So let's now engage the motors and slowly and incrementally move the extruder to see if we can get the hot end to dock properly. And unfortunately, we just ran into our first problem. The hot end didn't stay on the dock like it was supposed to. So when taking a closer look at it, it seems like the screw heads are a little too small and they're not able to grip the dock well enough. So let's go ahead and switch them out for these flange button head screws. They have a wider head, so it's going to give us a little more gripping area on the hot end, and let's see if it's going to work better. Just like before, we'll start out by doing a hand check by manually moving the extruder with our hand, and we'll do that several times just to make sure there seems to be an improvement. And I do see an improvement. It's definitely taken less force to pull out the extruder from the hot end than it did before. So now let's enable our motors and see if we can get the hot end to dock by sending motion commands to the printer. Now let's take a closer look at the extruder pin and make sure it's engaging well. Nice! And now the button head screws on the hot end. Wow, this is starting to look like this is gonna work. Let's keep moving along. Now we'll slide in ABS filament. And look at that, it looks like it gripped the filament. Now let's see if the gears will release the filament when the hot end docks. And would you look at that, they sure did. Man, I'm starting to get excited. So let's heat up the hot end and try extruding some filament to make sure the gears actually do grip the filament. And would you look at that, there's definitely filament coming out. This is getting really exciting here. Now let's try this with some TPU. TPU is soft, so let's see if this extruder can handle a soft filament. Wow, look at that, the TPU is actually extruding. I'm a little surprised, I was a little nervous with putting TPU in there. But it worked, so we gotta keep moving forward. Now I already assembled and aligned the second hot end and dock, so it's time to start doing some real testing. And it took some time to figure out and tune all the positions that the extruder needs to move to, but once the positions were measured, it was just all about writing macros with motion commands. And so let's run the macros to test the tool changes on the brand new tool changer. And it's amazing. The tool changes actually work. And at this point, I was excited and relieved. Excited because the idea was finally working, and I always love seeing projects work out after putting so much time and so much effort into them. To think that something is very challenging or almost impossible, and then you actually achieve it. And I'm relieved because this was for the first time that I had real proof that the tool changer can actually work. Up until now, it was just all in my head, and there was no real way to test all of the parts before you had them all assembled and aligned. The best thing I was able to do was just do some basic tests to make sure the parts weren't totally bad. But now the tool changer works, and I finally felt the relief that this whole project wasn't a waste of time and money. There's a future for it. And the best part is that the tool changing happens purely mechanically. There are no other motors, and the core design is very simple. Pins sliding on each other, lever opening and closing, and screw heads sliding in and out of slots. Yes, the current brackets are bulky, but this is just the first prototype, and in the future the design will be made slimmer and simpler. We just need some work to get there. So now it's finally time to start trying out printing parts with this tool changer and calibrating and tuning it. But before we do, let's look at the cost, because that's the ultimate question: did we achieve a cheap tool changer? So let's start at the top. 5 years ago, I bought a 3D printer kit which cost me $1,079.40, which included all taxes and shipping. Second, about $30 in filament to print all the parts and assemble the printer. Third, the metal extruder that I used the filament gears and the bearing and the pin from cost me $27.10. However, I could have used the extruder I already had, I just chose not to. 4. The second V6 style Hotend cost me $18.99. 5. The flanged button head bolts cost me $10.75. Now obviously I only used 4, but I had to buy the whole pack for the project. Next, the magnets cost me $8.99 and I believe I used them all. Next, the dowel pins cost me $8.79. And then lastly, the ball spring plungers cost me $6.95. Now, I bought them to see if they could work, but I didn't end up using them. But since I did buy them, I think it's fair to include them in the price. Which brings the grand total to $1,190.99. So yes, it's not all that cheap, but it still saved me so far about $800 over the Prusa XL. Now you might be interested in trying out this tool changer idea for yourself. And if yes, then check out the affiliate links below where you can find out exactly which magnets and screws and dowel pins I used. And now that we know how much this tool changer cost, it's time to start printing. I decided to start by printing a small calibration rectangles to calibrate the Z offset. Both Hotends would print PLA, the left Hotend would print in red, and the right Hotend would print in black. But unfortunately, I ran into some other issues that I wasn't expecting. For example, sometimes the Hotend would not pick up during the start of the print, or the Hotend would not heat up before printing, or the extruder would not dock the current tool before picking up the next. But eventually I was able to resolve them with proper startup routines. Unfortunately, I still had a big problem with the Z offset for the second Hotend, and it kept on coming back. It would seem like it gets calibrated and then that offset would no longer work. However, eventually things did seem to stabilize, and you can see the various printing results how eventually the black squares got better. So it was time to calibrate the XY offset for the Hotend too. Now to get started, I just wanted to get the XY offset close enough. So I started with crosshairs with alignment marks. The right hotend printed the black crosshair and the left hotend printed the red alignment marks. And the print came out well. So after taking some measurements and saving the XY offset, I proceeded to the second print to double check my alignment. But this is when I ran into some major problems. Take a close look at the right hotend that is docking. It failed to dock and crashed into the left hotend before I had a chance to stop the print. What a disappointment. Now I have to admit, this type of a crash would happen every now and then when I was printing the calibration rectangles. But over time they started happening more frequently, and at this point these crashes started happening on every print, which means it's time to stop printing and start finding out why. So let's take a look at the hotend. When I push on the screws, it wobbles quite a bit, and you can see the nozzle move around a lot as well. And there's a lot of side-to-side play when I pull on it side to side. It didn't used to be this loose. This is not good. Now let's try extruding and retracting some filament to see what happens. And when the filament starts extruding, the hotend rotates counterclockwise, moving the nozzle down and to the right. And when the filament retracts, the hotend rotates clockwise, moving the nozzle up and to the left. So this might explain why I was having some Z-offset issues. But why does the hotend no longer dock? Let's look at the slow motion video of the left hotend docking. Here's how the hotend is supposed to dock. But this is what actually happens. Look at what the hotend does. Sometimes the extruder would not slide into the hotend smoothly anymore. And then when the extruder starts sliding sideways, the hotend doesn't fully slide with it, and it starts to rotate, and when it does, it stays on the extruder. Now after trying a few things to make the tool changer last a little longer, it didn't work. So I accepted the fact that the plastic tight hole and slots are already too worn and not usable, and I need a better design to continue the single extruder tool changer. But if I didn't get a successful 3D print with this tool changer, how do I know that this single extruder idea works? Well, I sort of did earlier when I still had only one hotend. The first successful print was this simple cylinder. I printed it with no tool changes just to make sure the hotend and extruder were working well, and it came out pretty nice. And then I printed the same cylinder, but this time docking and picking up the hotend between every layer change. Now I did have a couple of failed attempts at first where the filament would get stuck, but then I was able to print this cylinder successfully. And yes, there was some oozed filament because I didn't have retraction set up. However, the rest of the cylinder looked pretty good as well. Which means that before the holes were out, the single extruder and the tool changing mechanism worked. So I am convinced more than ever that the single extruder tool changer is possible. We just need more time to develop it to be robust and reliable. The design that actually works will probably look pretty different than this prototype. And that's okay because this prototype is just the starting point. Now in the coming months I'll be working on the next version of this tool changer. And if you want to get access to my models and get updates as I make improvements, then click on the link below to sign up for the membership waitlist. You will be notified as soon as the membership launches, and you will get an exclusive 50% discount that you can enjoy as long as you stay a member.